So the next function we have, let's take a look at the class definition. Going back up here. So in fact, so we did the add functions, we did delete item, and so there's this function called findItem, and this is typical. I mean, these are all pretty typical functions for any container, right? You want a way to construct your container, the way to add items to the container, a way to remove items, and certainly a way to sort of see whether or not items are in them, for most containers anyhow. And so the way this works is that, well, given this function, well, it looks like it returns true or false. So if the value is in the container or list, return true, otherwise false, right? Otherwise return false. And so how do we use this? And so in main, like I can declare a linked list, call it my friends. I can do things like I can do a bunch of different things where I add friends into my list, and then later on I can ask some questions, right? So am I friends with Danny Trejo? If so, I can watch the awesome movie, or I can get some tacos from his taco joint. And so this is how we would use it. And so what I'm going to do is I'm going to leave this for you to implement, right? And so given this and everything we talked about, you should be able to figure this out pretty straightforward. I mean, it's more or less just taking the pieces we already talked about and throwing in here, and maybe reconciling a few things. But yeah, so I'm gonna leave this for you to do. In fact, though, does this idea, I'm sort of missing something here. So this find items function, shouldn't actually change the list itself, right? Because we're just looking for something and answering the question whether or not the thing is in there in the first place. And so let me go ahead and change this. One slight adjustment. Since this is not actually changing our list, let's make it a constant member function to just guarantee that this actually doesn't change the thing. And so let's change this here as well. There's a minor thing in terms of const correctness. And so yeah, I'm gonna leave this for you to do because it's a good exercise, and it allows you to sort of go back and sort of think about what the pieces we've discussed already and how that would fit into this particular function. Okay, and so the very last thing we're going to discuss, in terms of this linked list, we're going to talk about variations as well. But in terms of this linked list, since we're dynamically allocating nodes, we need to talk about how actually to clean up after ourselves, right? We need to, when we're done with this linked list, we need to have it essentially delete all the nodes it's already allocated. And so we have to be a little careful. And so let's go ahead and talk about that. So in destructing our linked list, well, let's take a look at what our linked list might look like. So let me grab a linked list. So our linked list might look like this, and so suppose we're done, right? We're done doing whatever it is we need to do with this container class, and so we want to we want to end the program. And so once we end the program, we want to actually have a mechanism to ensure these things are deallocated appropriately, right? And so the question is, how do we go about doing that? Well, it should be clear that on some level we want to delete every single node. That should be pretty clear. And so that sort of seems like we want to traverse to each node to delete the node in some way, right? And so let's go ahead and just use code that we have already in terms of deleting nodes, right? And so, well, in this case, we definitely want to delete all of them. So what code do we have that visits all the nodes? Well, recall the print items visits all the nodes, right? It prints every single node. So in this case, we would print cat, dog, rat. In this case, though, we're going to do something a little bit different with it. So let me go ahead and copy this, move it into our destructor. And so now instead of printing it, we are simply deleting the node at this address, right? So delete B. And so let's go ahead and just see if this actually does what we want with the data structure, or with what we currently have with the starting state. Okay, and so we declare a node pointer P, and so let me node pointer P, and it stores the value that's currently in head, and so that's already done here for me. And so we have this picture, boom. And so here we ask the question, is P null pointer? P is not null pointer, and so we delete P. And so this is the same thing as saying delete the thing at address X1 or 1000, and so let's go ahead and delete this. That's essentially doing this, right? I'm just moving it off the screen, and so delete it. Okay, and so now we have P, we dereference P well, there's nothing here to dereference, and so we can't do this. This is actually an error, and hopefully this would crash because this doesn't make sense. If this actually dereferences and does something, that's typically bad. We don't want that to occur. And so clearly, the way this algorithm is formed, it doesn't do what we want because it gives us a memory leak. So this is bad, right? And so what do we want to do here? Well, first of all, we don't want to lose this, right? In deleting P in this way, we lost information. We lost this, and so we can't get to this to delete it the next time around. And so why don't we just save that information, right? Why don't we change this a bit? Let's go ahead and create another pointer. Let's say, I don't know, n maybe, right? And so let's call this guy n, and have this save this, right? We want this to store x1400. And so when we delete P, boom, we still have a handle onto this. And so we could then move this into P, and so we can restart the process of the while loop. And so let's go ahead, how would we do this, right? And so before we delete P, let's go ahead and declare another node pointer, n, have this store, well, let me bring this back, right? So what do we want it to store? We want it to store 1400, which is currently stored within P's next. And so equals P's next. So that will put the next node address here. We can then freely delete P. Boom. Get rid of it. Boom. And so we don't want P to go to P's next because it doesn't exist any longer. We simply want P to go here, which is here now. And so we change this to N. And so now, then we go ahead and update P to equal N, which is x1400. And so the picture becomes essentially this. And then we go back to the top. Is P pointing to a valid node? Yes, it is. Or that is P null pointer? No, it isn't. And so we jump into here. We create this node pointer N. Oh yeah, so between every time we go through this while loop, N will go away and be reallocated. But I'm just gonna leave it here for convenience sake. So N will store 800 in this case. 800, and so that means that, and so we can delete P, and so this goes away. Boom. We update P to be N, so this gets x800. Boom. And then we go back to the top of the while loop. I actually need to update the picture. Choink. We ask the question, does P point to, is P null pointer? No, it isn't. And so we go into the while loop, we create this thing called N, it gets P's next, which just happens to be null pointer, PTR. And so now we, well, get rid of this. This actually goes off to the end of the list. We delete P, so this goes away. Boom. We set P to be N, so N is null pointer, so P gets null pointer. And so this points off to the end of the world. And then we go back to the top of the while loop. We ask the question, is P null pointer? Or is P not null pointer? No, because it is null pointer, and so we're done. And if we look at the picture, everything's gone. And so yeah, looks like we've successfully deallocated everything that was dynamically allocated, and so we should have no memory leaks based on this algorithm. Okay, and then there's a bunch of different ways of doing it. You don't have to do it in this way. It's just whatever you do, you just have to make sure you don't have memory leaks. Anyways, so that's how you destruct a linked list.